Okay, 15 years of policy routing. Why the heck did I think I was going to do this anyway? So let's go back to the retro and see what we thought the problem was with policy routing. Well, actually, in 1986, 85, when the previous NSFNet was running, I got to visit the last 2 months of it. I joined the NSFNet team in 87, actually in May of 88, and that NSFNet got to watch routing IGP storms go from one side of the country to the other side of the country and back. And routing was so unstable. If we think routing's unstable now, I could watch literally the ping times come and go like waves upon the sand, and it wasn't much fun. That's why some people said they were going to take a break. So to try to limit it, we tried to set, Hans van der Bron set up what we call policy routing, which is, I'm going to turn a deaf ear to what you just told me unless you told me ahead of time you'd be telling me that. Sounds like repetitiveness, but that's what policy routing is. It started out with EGP, it went to BGP, but it had to have a component where we had configurations. So Dave Crocker once asked me if I liked the life of configuring the internet. That was because I used to configure and make sure or run the team that actually kept what routes went where. But we tried to birth IRRs and RPSL. So let's go into policy routing and see where it is. And I will be like Dino, having to watch my time carefully. Again, earlier I told you what's new, and that routing seems simple until you look at all of those routes, and that we're still changing. If you look at EGP, we started that back in 81, and I was never so glad to have something as when I got BGP. Because what we used to have is with a grand total of 200 routes, the EGP routers would freeze up those old NSFNet routers, and they just sort of pause for station identification while routing was run. So BGP was incremental because in EGP we used to dump everything at once. And that really worked and helped us grow until we needed things like BGP 3. By the way, BGP 1 and 2 were sort of funny because the first one just sort of didn't make it out of the lab because it didn't make through the test, and the second one was pretty much what we ran. But BGP 3 actually allowed us to point default to some big core. IDRIP was the ISO version of it, and BGP 4 was finally when we actually tried to do CIDR, as we had that little traffic flip way down before this. Down at the very edge and far left at that first line, see that little tiny, teeny flip down there? That's what we had. And we did CIDR. Well, we then tried to fix the iBGP mesh because somehow we thought that full mesh, full route distribution was going to scale. Well, it scaled till about 10 or 15 routers, maybe 20, but at 200 we sort of toasted. And then we had MBGP. So to fix the iBGP, we had route reflection and confederation, and we're still fixing problems. So let me quote one of my friends. There's Lyman Chapin, who helped with the ANSI X3 and really was a good guiding light for us all along through this period. He said, on the surface, routing is simple. It's just a matter of figuring out how to get from there to here. But 20 years of routing and research with different protocols has just found out that it's anything but simple. But on the other hand, there's my other quote, fortunately, we've been able to make progress, we've been able to do well, and not suffer too damage with the past wars and all those indecisions that Dino talked about. So let me tell you Dave Katz's viewpoint. Dave Katz gave a wonderful NANOG presentation on IGP scaling and sub-second convergence and what really matters. And I should really urge you, if Dave, go back in the NANOG directories, look at Dave Katz's work and just pull it back in. His comment was in 1990 we had correctness, stability, scalability, and speed, choose one. In 1994 we had correctness or stability or scalability or speed. You got to choose two, and it was correctness and stability. In 95, we added scalability. By 2002, we'd probably got scalability and working speed. And with many proposals we've had in 2002 and 2003, my opinion is we're trying to add high availability, nonstop, the fact when you reload your configuration, you don't dump the network, many of these pieces. Now, I think, as Dave did, we're actually starting to see the fact that after 10 years, maybe sometimes we can get it right. 3 or 4 versions of the same protocol, maybe we can get it right. And the engineering tells us what things provide speed, scalability, high availability, and stability. And the only effect on these routers is we hope it's just a slowing of convergence, not a crash and burn. And we can actually manage configuration without taking that pause that doesn't refresh. So why policy routing? Just to go back through the basics, what did no storms in the network mean? It means instead of having routes that travel like my friend, the animation, they hit a wall. And that's what policy is. What was the policy in the NSFnet? We had a merit database. It dumps things. And it was out of my desire of not being able to type. Anybody who's watched me type knows it's a attempt to watch lots of things happen, but anybody could make a mistake, and the configurations that many people do still are CLI based. We created configuration files. Why an IRR? Well, as Andy always told me, that's public BGP policy. And some policies are private. It makes you wonder what happens to networks in the privacy of their own interconnects. The outgrowth of configuration files to the Internet NSFnet brought us that. And what was RPSL? RPSL and flat file transfer is how databases used to share information. Now, in the late 95s, we thought a public database might grow into a public service, but people in large carriers that are not necessarily cooperating but competing don't always want to share information. So again, the public policy is what we need to get by, and the private stuff is what we need to have business. Now, what's happened to BGP over the years? Well, we got so old and dusty that 2 years ago, the ISG said we had to rewrite it. That's been an interesting experience for me. Come see me afterwards, buy me beers, whatever. There's also been 2547, which is putting all the instrumentation for signaling inside of BGP. And there's so much that once you start, people said, is it abuse? And Alex has said, we should restrict this, we should stop. Yakov, on the other hand, says, if you pay me to put Shakespeare inside of BGP, I will put Shakespeare, as long as it makes money. So I think we have two different things. I think if you ask me what I think, is it going to make money? Is it going to keep the, is it going to help us all keep our networks up and going? So I'm sort of the whatever it takes to get the job done. Alex also said maybe we should limit it to routing security or things that are limited. Now, people may or may not know that BGP has problems. I suspect you live with it daily, but just to make sure everyone didn't miss all the problems set, we have convergence problems. We do have MED election problems. We don't have a general spec for ECMP paths or traffic engineering. You can see Cisco or Juniper or your favorite vendor to see proprietary ECMP. There is inflexible boundaries inside of BGP. Mike Odell says you should have less. There's a lack of policy verification prior to load. There's no ability to sync BGP policy. And BGP security doesn't scale to multiple millions of routes. More about that later. And perhaps we might overload it. I've gone through this, and with, like Dino, I will skip on to make sure we stay on target. Now, once the current drafts are coming to fruition with BGP and route reflection, we have a whole new crop that we've already deployed, which is BGP for V6 multicast, graceful restart. So as John Scudder put in his first note when he wrote this, I'll be back for BGP routers, extended and ORFs. We're about finished with the CEAS and ORF and AS path deployment. And by the way, this is probably your friendly person saying, if you have a problem with one of these, we're finished with the base BGP spec, at least that's what I've been told by my friendly chairs. If there's problems with your ORF or your CEAS codes or your router identification, come see me, tell me what it is, because we're about to send those on their way. and start a whole new set of BGP IDs. Some of the new ones that are coming on the landmark are AFI and SAFI isolation. There are AFI-SAFI drafts which say, oh, let's not share all these VPNs on the same TCP connection. Duh, maybe that might be a good idea. Maybe there might need to be some next hops that are better. Another thing came from the carriers that said, you know, I have two types of problems. One, somebody screws up and sends me a full dump of the internet routing table. Or two, I'm monitoring a VPN and the VPN says, oh, I just crawled over my limit and I got one configuration knob. Stop having a max prefix. So this set of drafts are negotiations, so maybe if you didn't guess it right or the customer didn't guess it right, you could actually negotiate it. There's additional information to try to yet fix the MED oscillation, and there's security configuration requests from our friendly Bogon team, but you've seen Rob Thomas and you know why we need it. Then the scalable security. Now, the first thing is those Homeland Security folks still want us to have secure BGP. It's hard to secure a lying protocol. BGP is a lying protocol because it whispers about what it has from its neighbor. SOBGP, SBGP, you know, there are some statistics there, but I like Randy's quotes best. We'll just have to wait for the next generation hardware because this puts such a load on the routers. And in a couple years, they'll be ready. But Randy brings up a good point when he talks about here's security. We could do it with SOBGP or SBGP by adding things. The real issue is, does the security scale in order not to overload our routers? And I think that points out one thing that we've learned over the years. As Mike Odell says, if it scales, all else follows. Or Tony Lee that says, better a good implementation of a bad protocol, meaning something that works and keeps going, than a bad implementation of a good protocol. It is all about engineering. Well, why do you want to improve security? Well, because otherwise folks are going to be down looking at us, but more than that, they're going to spend too much money on the security instead of on the network, the more costs we can drive out. And another point of security is, when is it bad security? Because without tighter controls on the configuration of security, it's difficult to find the anomalies without the errors. Now, there's some really good people trying to sort through all of that, but if we just fix the configuration problems, that might work. Why fix complex policy? Well, maybe you like writing lots of complex policy, or maybe you'd like simple policy. But the real measured things, and I gave some things which are independent research firms that say maybe 1.1 to 1% of some corporations' revenue is due to misconfigurations, mostly 50% to router devices, maybe mostly servers. But it's real important. If we could squeeze this out, we could get more. Now, another thing we've talked about over the years is next generation routing. And I started to put the time then we started to talk about convergence problems in BGP. 99, I think it even goes back to 1994, but I couldn't find all my notes. Where you have convergence problem, we've talked about it. I think it's died down recently because, as John puts it, there's extra fiber. When it comes back up, some of these problems will return. So what do we need for the next generation? Manageable security, scalable manageable security, reducing the management cost, removing the bottleneck, all keeping going so we can keep doing it. Now, I think in the next slide, I'll give you some things that are actually a reaction to stopping going forward with BGP changes. I think we change till we get everybody's BGP working in the right way for the right situation. I think these AFI-SAFI drafts are really important if they provide you with something that keeps your network going. And I'd love to hear more. I think people have been getting a mail blast for me in some of the ISPs saying, please tell me if you think that we've got a problem, what you have a pain with, because we're about to turn the tap open on some changes to BGP. Tell me what you like. Because in the history of BGP, that's really been the key. All of the NANOG folks, all the regional techs have really guided BGP. And in many cases, that's why BGP or DNS are at the source, at the center of internet infrastructure, because all of you have worked. So I think one of the next slides are some research, because I refuse to give up on changes. I don't know if they're good changes, but I'd like to find better things. So, I've tried to see, if policy is a problem, is there some new algorithms we can have? If IBGP is the problem, can we go to a replacement of IBGP? Can we go to securing data, BGP routing data, at something less than an extra component? I don't know if I got the answer, but what I'm sure is we can keep changing policy routing to keep ahead of the curve, as the guys as John Curran, as Doug Humphreys, as many of the people say, we're smart technical people. It isn't the technical issues that are going to get us. So give us input. Policy routing is your ever-changing BGP. It will probably, look the same, look different. Policy routing can limit storms. It has probably provided us security over the time period, over the duration. BGP is a TLV carrier, and convergence matters. So, Dino, it's your turn for multicast. Hopefully I've got all the right things here. So Dino's now going to come back and give us multicast, which you got to give him extra credit, because he's not only went through one long talk, he volunteered to do two. Yay! And he does an awesome job. The first one, I hadn't heard some of the stories he'd had, and I thought I knew every story there was.
If the last talk bored you, this is going to bore you more because it's multicast. I'll take you back to the late 80s when the origins of multicast pretty much started. Again, this is something that I lived. Then I'll look at some of the requirements from the early 90s, which caused the multicast protocols to be what they are today, and look at the protocol evolution, where we are now, where we're going to go, in the closing summary. So link local multicast addresses date back to around 1989. Those various protocols existed back then. They were actually sending IP multicast packets to do whatever they're supposed to do on single links. These sort of packets were not forwarded by routers. IGMP v1 implementation started appearing in host stacks in the early 90s. Router vendors came next with a v1 and IGMP v2 implementations. Early routing protocols from around the 1993 timeframe was DVMRP and MOSPF. And then the next generation wave of protocols started in the 94 timeframe, which was CBT, dense mode PIM, sparse mode PIM, and IGMP version 3. Interdomain related protocols in the later 90s, BGMP and MSDP. And then there's been some auxiliary protocols, MZAP, MSNIP, and the reliable multicast protocols from the RMT working group of the IETF. MBone was a wonderful experiment. Everybody learned quite a bit, not only on how to build multicast networks, but how to build applications and how to do voice and video over IP. Consolidated a number of protocols needed to happen. IGMP v2, PIM sparse mode, and DVMRP was pretty much running on the MBone. Tunneling, the MBone, if for those of you who don't know what it is basically multicast capable hosts and routers that run over an IPv4 unicast infrastructure. A lot of the links did run multicast, but the ones that couldn't, basically GRE and DVMRP tunnels were able to connect them together. That was hard to manage after a while. In the mid-90s, ISPs went native. They actually turned on PIM on their routers, and they ran them natively. And this is when we pretty much moved from the MBone to a native infrastructure. At that time, it was mostly IGMP version 2 and sparse mode PIM with MSDP using to find sources in other domains. At the same time, brokerage firms and in the enterprise turned on multicast for, the brokerage firms turned it on for stock trade, quote distribution, and the enterprise wanted to do some desktop conferencing, distance learning sort of things. So the requirements, the initial requirements was to try to build an infrastructure to allow desktop conferencing, distance learning or event distribution like rock concerts, radio stations, those sort of thing. And the brokerage applications were a very important application because the revenue, they were high revenue generating sources. Non-goals were resource discovery. Even though multicast protocols or a multicast infrastructure could provide resource discovery, it wasn't really high on the goals list, so I'd consider it a non-goal. And ditto for cache coherency sort of schemes. And I also say that the Mother's Day problem wasn't really a goal. My definition of the Mother's Day problem are there's, millions of mothers across the world that talk to their 2 or 3 kids. So this is lots of groups with very small members. Does that application require multicast, or will replicated unicast serve its purpose? So we weren't trying to solve on that sort of scale. VAT, VIC, and WB were the applications being used in the early 90s to distribute IETF working groups. The content providers were interested in reaching very large audiences because reaching large audiences meant advertising could hit more eyeballs. This was a good revenue generator. Brokerage firms were using UDP broadcast. Their Sun workstations were melting down because even though they wanted transportation securities, they were receiving utility securities at the same time because everything was broadcasted everywhere. When IETF was developing PIM and CBT, at that point, router states seemed to be the biggest technical hurdle. CBT helped because it was a protocol that only implemented shared trees, so you would have one distribution tree per group. But it could not always give you low delay paths, because if a source and a receiver weren't close to the root, you would always have to go through the root, and that could give you a suboptimal delay. PIM then said, well, we'll have both shared and source trees so we can deal with low delay, more state versus higher delay, which could be less state, or less delay, less state trade-off. So the lessons we learned over time was CBT probably didn't have enough functionality to make it work in the internet as we know it today, and PIM shared tree to source tree switchover probably was too dynamic. We probably didn't need it to be as dynamic as we first were trying to solve. And at that point in time, the bursty source issue wasn't even known to be a problem until we started looking at the protocols. And we learned that the protocols had this sort of data plane, control plane dependency, which was probably one of the architectural pitfalls of multicast. This is what makes unicast routing actually scale, is that you have a separate control plane, and then the control plane is set up first, and the data plane can act on that. In multicast, state was created based on receiving data, and this is always hard to implement. Some other requirements, at the time when I was working at Cisco, the Cisco customers didn't want to change their unicast routing protocols just to deploy a multicast service. So they wanted the multicast protocols to be able to sit on top of what they already had. They also wanted it to work over AS boundaries or IGP distribution boundaries. At that time, there was a lot of IGRP, OSPF, and RIP in the network, and a lot of people were running multiple ones. They wanted to have the routing protocol run on top of all that. And some customers wanted a broadcast mode, especially the brokerage firms, because most of the packets were going to go everywhere, and they wanted you to handle the 10% case where packets didn't need to go to a certain part of the network. And that's why we started with a dense mode protocol. Routing domains didn't want the inner working issues that they had with unicast protocols. So the question about should we have a multicast IGP and a multicast EGP split? Should you have one for intra-AS and then use a different protocol on top? And it turns out that they didn't care about that as much as they did for unicast, and that a single multicast protocol that built distribution trees would be sufficient. And we could do the policy at the BGP level and at the PIM join level. Transition would be incremental, so unicast protocol had to be reflected on a different, the unicast protocol had to reflect a different topology. So there was going to be a multicast interdomain topology and a unicast interdomain topology. Or if the cases where the topologies were absolutely congruent, the policies were possibly different, so you would still need to take different paths. So the protocol evolution went like this. We started with flood and prune protocols, and DVMRP and PIM dense mode were the two protocols. This is where packets were sent everywhere, and you only prune where the receivers are not. But of course, when you're Typically doing a conference across a large geographical area like the capital I internet, it's mostly sparse. 10 people collaborating over the internet, you don't want to flood and prune everywhere except for 10 people. So you have to use an explicitly joined protocol where you send packets only where it's being needed. And PIM sparse mode and CBT could work to solve that problem. The only problem with using shared trees, which both of those protocols used, is that the rendezvous point or the root of the shared tree being able to distribute that information across the internet was a problem. This is, again, a way where you want to push the information out. The RP to group mappings had to be pushed, and the dependency on the root had to be given to a third party. ISPs did not like this at all. They knew that the push would not work, and they knew that depending on a rendezvous point in their competitor's domain would not work. Just think if you're in an ISP and your source can't talk to your receiver because the root is in your competitor's domain. So this was just not going to, this was a non-starter. And hence we went into the interdomain sort of protocols like MSDP and BGMP, and they could work to solve the problem. So what happened was DVMRP dissolved when workstation-based routers were replaced with commercial routers, because the commercial routers were supporting the native protocols at that point. PIM dense mode was limited to broadcast applications in brokerage firms, and sparse mode worked out because it was the only one, the one tree distribution protocol that was used across all multicast capable routers. BGMP, there was an attempt at looking at BGMP, but it turned out to be too complex to run as a separate interdomain multicast protocol on top of PIM. So it turns out that didn't go very far in terms of the deployment. MSDP was used instead, so you can keep your rendezvous points local to your domain, and you could distribute the source information. The sources that were active in your domain, you could tell other domains, and if they were joined to those groups, they could just PIM join back to your domain. And MBGP, or multi-protocol BGP, like Sue alluded to, is used to be able to deal with the non-congruency issue, and it's still pretty much in use today. So where we are now, we run PIM sparse mode, where people manage their own RPs. Domains discover sources and other domains by running MSDP between their RPs and the RPs in MBGP peering domains. MBGP is used in parallel with BGP to find paths to multicast sources, and this form of multicast is called any source multicast, where it's actually using the traditional part of PIM, where you use both shared trees and source trees. Where can we go in the future? Well, IGMP version 3 implementations are appearing in hosts now. That means hosts can join and leave channels and not groups. And a channel would be defined with an S, G pair, where S would be Finding Nemo and G would be Disney. Or I should say Finding Nemo would be G and the source would be Disney. So if you wanted to subscribe to different channels at the same location, you could use the same source address. And then routers can support source trees only. They wouldn't have to support shared trees. And then sources would have to learn, sources are learned at the application level through a directory mechanism or HTTP. And this form of multicast is called single source multicast, or SSM. This doesn't mean that a particular group can only have one source. It means for each distribution tree, each multicast route, there's exactly one source. And that's called an S, G entry, and this is not a new concept. This was in PIM and DVMRP day one. So there's another model you could use also, is hosts can join groups like ASM. They don't join channels, but they join groups. And then routers can forward packets on a bidirectional shared tree. And this is, a lot of the spirit came from CBT. What you do is you set up a bidirectional tree. When an RP is learned for a group range, you decided if it should be run in BIDIR mode or non-BIDIR mode. But basically the RP is learned for a group range, and that defines the sender branches. And when branches are joined, those define the receiver branches. And in a bidirectional tree, you can have low delays between your source and receiver, because what you're doing is you're routing a packet up towards the RP, but if there's any receivers in this neighborhood, the routers turn them around. So you don't have that third-party dependency problem as you did in the ASM case. And this is coined as BIDIR multicast. So closing summary, we've gone from dynamic switching of tree types to using a single mode per group range. So PIM sparse mode now is trimodal. For IP version 4, 232/8 was assigned as an SSM group. So the routers know what to do when packets are being sent to that group or joined to that group. That means PIM will use source trees only for that group. There could never be a shared tree route for a 232 entry. And then BIDR RPs are learned when group ranges are learned via RPs with a BIDR flag set in the various ways via the bootstrap mechanism, the auto RP mechanism, or static. So if it's not an SSM group range and you learn about an RP and it's not flagged as BIDR, then it runs in ASM. So those are the pretty much three modes. And those three modes can actually run in intradomain or interdomain. So final summary, where we are with IPv4 multicast is trimodal is the options that you can use and are available today. And MBGP is still a necessity because people want to give different policy to multicast as they do to unicast. But what we're seeing for IPv6, we're trying to make multicast even simpler. We've gone through there's many war stories on how complex this stuff was, and the developers recognize this and are trying to go much simpler. So we're looking for a dual mode sort of operation in IPv6 where we use SSM for intradomain and interdomain communication. And we can use BIDR as well. The brokerage firms really like bidirectional trees because they have a lot of sources coming and going, and they don't want the state to be created on demand. So they like to use shared trees, and they like the low delay paths that are associated with a bidirectional shared tree. So BIDR as intradomain is going to see a lot of increase in deployment in the coming years. And it could possibly be used for interdomain now too if you're worried about your S, G state problem. Also, MBGP will still be a necessity, and you won't need MSDP anymore because now if you run SSM as interdomain, you don't have to discover your sources. The hosts are telling the routers where the sources are, and the routers just propagate joins towards the sources. This way we can get multicast to become much simpler and therefore more reliable. I don't know if anybody's remembered this t-shirt, but this was when the M-bone was pretty active, ATM was on an uproar. And of course, everybody knows what 53 is, right? That was the cell size for ATM. And of course, the famous quote from Van Jacobson. That's all. Thank you.
Thanks, Sue. I'm actually going to go back a little bit further than 10 years when I start my discussion of security to an early communications technology. This was a way in which I encoded a kind of packet, if you will, in which I encoded my applications. It was an unreliable protocol with a long round trip time, and if the packet was dropped by the provider, I had real problems. I mention this because a lot of the early security stuff goes back to that era, 30 years ago and more. In the days when mostly you didn't have networks, security seemed simpler then, since the only problem you had was corrupt outsiders or physical attack. And physical attack was a problem that was reasonably well understood, having been several thousands of years of coping with that. For that matter, several thousands of years of coping with corrupt insiders. Yeah, there was connectivity way back when. In 1970, I was running a star network for the City University of New York, because the computer at our campus was serving as the hub for the remote job workstations entry. And the reason that worked reasonably well, not that anyone paid too much attention to security in those days, though there was more than you might think, is a very limited service interface. What you could do remotely wasn't a lot different than what you could do if you were present on site. And security was mostly concerned with accounting. Were you paying for the service? Networking changed all that because one thing, hosts were more exposed. You could be exposed remotely, and the richer your service interface, the more you were exposed to, and the network itself had to be protected. Now, the network itself being protected was something that my employer had rubbed in its face in the mid to late 60s with the so-called blue boxes. In-band signaling was abused. People could rip off telephone service. But that was more or less the only service that was available on the phone network at the time. And so it was not, in some sense, not too hard to deal with. You know what the threat is. The internet is really great at a really rich service interface, And that's why we have so much more serious problems today than we did before. But we've also got the problem of protecting the network itself. You know, I sometimes joke that when I speak of network security, I'm lying because, you know, highway robbers don't steal the pieces of asphalt that make up the highway. They rob what's going over it. With the network, we've got security. We've got to protect the network itself, and that's a lot harder than just trying to protect the hosts. You know, so what is security? What is it we're trying to do? Classically, we had the Trinity: confidentiality, integrity, availability. Well, it's all still there, but in a different form. We want to stop not so much confidentiality violations, quote, just use crypto, unquote, a point I'll return to later, is we want to block any sort of unauthorized access to any host. Why? Because most hosts are not locked down adequately from a host security perspective. For one thing, the operating systems are pretty poor at doing that. For another, the really sensitive data is often widely exposed. And finally, often what's most important is the host's identity itself, whether it's a cryptographic identity, if you compromise the host, you have access to its keys, or topological, you're inside the firewall, you're inside some trusted perimeter. So we've lost confidentiality as a main goal for most of the security stuff and changed it to one of access. And that's a harder problem. Cryptography doesn't always help us there. We've got privacy. I'll return to that point. Web servers are a particularly bad case for both of the above and most of these. We've got to prevent abuse of network bandwidth, the DDoS attacks, and the out-of-band attacks. I won't say a lot more about out-of-band attacks. I won't say a lot more about a number of my and your favorite problems. I don't have enough time. I'm glad so thank you for not having me go before the break. It's a bad thing to stand between geeks and their food, especially their sugar. If we go back just about 10 years when password sniffing suddenly became a major threat. Why? Because it was workstations that were on major backbones that were compromised and turned into sniffing stations. Well, we know better today. We don't put workstations on these backbones. Fortunately, it's a lot harder to do so today. You don't have the kind of broadcast media today connecting your high bandwidth routers, but it's also we've learned a little bit about where to put certain dangerous sorts of things like an easily compromised machines. To be sure, the bad guys have graduated from hacking workstations to hacking routers, but we still have some better level of defense. Wireless makes it worse. You know, I should take down my slides and just put up the DSNF. I'm running DSNF. After the demonstration that Bill Fenner, Randy Bush, and a few others and I put on last time, you'd think that I'd see fewer passwords today. No. And it's not a good idea to use SNMP or Telnet to query your production routers from NANOG. I know I'm not speaking hypothetically. But even if it's a wired net, you get ARP spoofing and monitoring ports. It's bad out there. That's one of the things we can fix with crypto, though. There are protocol weaknesses like TCP/IP sequence number guessing. We've got more complex protocols today. TCP is relatively easy to analyze compared to, say, SIP or NetBIOS or H323. We've got DDoS attacks. We've got worms and viruses, our favorite social abuse of the internet. Click here to infect your machine. People do it. You could send out a virus that said, click here to infect your machine, and people would do it. And then there's buggy code. And buggy code is probably the worst problem. We'll come back to these points. Privacy. Sites know a lot about you. It's amazing what we learned, especially if you can correlate things. A bunch of my friends have signed up with a social networking site, Orkut.com. It's an affiliate of Google. You read the privacy policy and it explicitly gives them the right to send your personal identifying information to Google, so it can presumably be correlated with your Google queries. Talk about that as a privacy violation. They don't promise not to use it for marketing. They promise not to give it to third parties for marketing. This is a fairly scary thing, and you then fold that in with the Patriot Act. I suspect I and a lot of other people last week were Googling for how to make ricin. Gee, I'd love to have that tied to my address and phone number. How do sites protect this information? Many of them don't. That's often their business model. Web servers are in some sense the hardest security problem we've got because they're so hard to protect. The most dangerous service, port 80, is the one that you can't firewall off. That, by definition, is the purpose of the machine. It's the one you can't block. And why is it so bad? Because buggy code is the biggest problem on the internet, the biggest security problem on the internet, and it's not going to go away. And web servers, by definition, are running lots of code, most of it buggy, or potentially buggy, you don't know, especially all the locally written scripts, the CGIs, the ASPs, that haven't had the benefit of lots of eyeballs in the open source model or a structured development quality assurance process in the closed source model. Either way, it's locally written and probably buggy. Buggy code is the oldest unsolved problem in computer science. I'm quite confident that will remain that way at least for the rest of my professional career and probably for very long thereafter. A National Research Council study I was a part of a few years ago looked at every CERT advisory issued through 1998, say the first 10 years of CERT. 85% of the advisories described problems you couldn't fix with crypto, even conceptually. Most of these advisories were buggy code problems or configuration errors. We're not going to get away from that problem, and we do not have any easy fixes. So here I've listed all the defenses that we have. Let's be a little more optimistic. There are a few things we can try: protocol analysis, crypto, black hole routing, and firewalls. A few others, mostly less important. Protocol analysis is one of the things I don't get paid to do in my job as IETF security area director. It's hard to look at a protocol and say, here are the security holes. You know, it's kind of like testing. Testing doesn't show the absence of bugs, it shows the presence. I can find holes in protocols. I can't show that there are none. The job is a lot easier for a point-to-point protocol. Why, if nothing else, you bolt on some crypto? I may not be able to get rid of the holes, but at least I can restrict them to a couple of parties. Multi-party protocols are very much harder. The problem with BGP isn't securing the point-to-point connections. We know lots of ways to do that. You know, we've got the BGP TCP MD5 hack, which is theoretically not very good, and practically it's quite good. But that's not the real BGP security problem. The real BGP security problem is this guy 17 hops away is announcing some address. You have no idea if the AAS path is accurate or bears any relationship whatsoever to reality, because it came from 17 hops away. Think voice over IP with all the SIP proxies and so on. There are lots of parties in there you have to trust to carry the call correctly to the right party. That's the key. Authorization is the hard part. Who has the right to connect? Who has the right to send this data to advertise this resource? Again, it's very much harder for multi-party protocols because you don't know who all the parties are. I first became known to some people in the security community when I co-authored a book on firewalls. And a lot of people did and do really resent the concept. So I'll come to it in a minute. Just about 10 years ago, Phil Karn and I had a very lovely and informative debate at the IEEE Security and Privacy Conference. Phil took the position that firewalls were bad, and I didn't take the position that firewalls were good. I took the position that firewalls were necessary. I'll come back to that in a moment, but more than one friend of mine has said, we don't need firewalls, we can fix the problem with crypto. It shows a misunderstanding of what firewalls are about. Crypto solves some problems. Crypto is a very important part of some problems. It gets rid of the DSNF problem. I use crypto from here. I'm using crypto right now to read my email. And we had some of the connectivity problems this morning. In order to connect to my office back at Florham Park, I set up an SSH session to Seattle, to a machine in Seattle, and then I tunneled the real SSH session that I wanted to Seattle and back to New Jersey. Double layer of SSH. I felt really secure, but at least I could get my email. Crypto is hard. Not just the crypto protocols, though those are hard enough, but managing them. Who was allowed to talk to whom and when and under what conditions? How do you get the keys? It's authorization all over again. There are several successful uses of crypto on the internet: SSL, to some extent IPsec, and SSH. And there's secure email, which from most perspectives has got to be accounted a failure. It's instructive to look at why they succeeded or failed. SSL technically is lousy. Oh, it's good at securing something point to point, but it's mostly a fig leaf. It's safe to shop here and spend your money here because your connection is encrypted. Encrypted to whom? I'm asserting 99.99% of consumers don't know what a cryptographic certificate is. I suspect I could add at least one, probably two more nines after that decimal point. They don't check certificates because they don't know what they are. If you told them a website had a certificate, they'd want to go there in person to go look at this frame thing hanging on a wall. If they knew what cryptographic certificates were, they probably don't know what root certificate authorities are trusted by their browser and why. Why should your browser trust, Mafia Incorporated's root CA? Well, at least at one point, the reason that your browser trusted was because your browser vendor accepted a large sum of money from the root CA vendor. Matt Blaze has observed that third-party certificates like this are very good for protecting you against anyone from whom the CA won't take money. But it served a purpose, and it did stop a real ill. It stopped credit card number sniffing. Given the experiences we had 10, 11 years ago with password sniffing, we certainly would have seen credit card sniffing today. Not on the backbone, but nearer the edges. Hasn't solved the problem of credit card number stealing. Instead of picking them up retail one or two at a time by sniffing, the bad guys hack the servers and collect the credit card numbers that way. But we've moved the problem someplace else. Steve Kent has observed that insecurity is like entropy. We can't destroy it, but we can move it someplace else. If we're good, we can protect that other spot better. IPsec is moderately successful. It's moderately deployed these days. Multi-vendor IPsec is a lot harder than it should be. Go back to what I said a few slides earlier about the crypto management problem. One of the reasons it does work for the VPN case is that the authorization problem is pretty easily solved. You get your credentials from the site to which you're connecting. IPsec has not lived up to the promise that Phil Karn and I and many others had a dozen years ago when we thought it could protect a lot more point-to-point communications. Why? You have a secure connection to someone and you don't know to whom. Secure email is largely a failure. It's only used by uber geeks for the most part. It's hard to use, generally needlessly hard to use because user interfaces are really bad. More to the point, where do keys come from? How do you know it's the right key? Many models require central deployment. Central deployment is not something the internet is good at. And people don't perceive the threat and therefore haven't been willing to go through the pain. SSH has been deployed more operationally, certainly among the geek class. You're not going to get most, Joe Sixclick to use SSH, but it's deployable because it's decentralized. I don't need anybody else's infrastructure or permission to set up SSH between any pair of machines where I have control over one of them. This is a very important point. It made it deployable. You don't need a key server. You don't need authority. You just do it. And it solves other problems. It tunnels other protocols. It's easier to deploy than IPsec. You don't need kernel mods or hardware boxes. And it deals with the perceived threat model. People who use SSH understand exactly what it is they're protecting against. DDoS, we do not have good defenses against. Go. Best defense for many people is let's null route the victim. If the bad guys want to take the victim off the air, good. We'll help, but avoid the collateral damage. We don't have a good defense there. We need one. We need a deployable defense. This is the attack today where the network itself is at risk. We'll probably see other attacks where the network itself is at risk. I'm not going to try to predict what they are. I'm a pretty lousy prophet, but rest assured they will come. We have firewalls. Firewalls are our best defense against buggy code. The purpose of a firewall is to keep the bad guys away from the bugs. It's not that I like firewalls. They're not a network security device. They're the network's response to the host security problem. Firewalls are a damning indictment of the state-of-the-art of software engineering. By the way, those two lines were taken from my slide from 10 years ago in my discussion with Phil. It hasn't gotten better. But firewalls are failing, and that's bad because they're one of our first lines of defense against a lot of these attacks. The big firewall at the front door, border control model, doesn't work because we've been too successful as internet service providers. We've gotten lots of connectivity. It's going through or around the firewall to too great an extent. We're running too useful a network. We've got the mobile host problem. Most of the machines in this room are going to go back home and connect to their home networks in a few days, possibly bringing any infections with them. Remember the worm problem at the last NANOG meeting? We're lucky that this month's worm wasn't of quite that type, right? I don't know, do we have any instances of my doom here today? Probably. Split use hosts, the telecommuting machines. How did Code Red and Slammer get inside most corporate nets? It did. So what do we do now? The threat's not going away. We don't have major new defenses on the horizon. There are no new major crypto protocols that promise to solve all our problems coming up. We have to leverage the internet's strengths. We can usually secure special purpose hosts in ones and twos. The problem is manageability and scalability. Quote Mike Odell, the internet scale is the only interesting problem. We need a scalable security solution. That's what firewalls were supposed to be. We do not have another solution that's deployable today to secure a large number of hosts. It's easy to say no with the packet filter. It's saying yes in a secure fashion that's hard. Crypto helps, preferably decentralized. But sandboxes and hosts use internet appliances. I don't worry about an internet phone running Outlook Express. It probably doesn't. When it starts talking too much to other things, then I worry. Things that won't work. ISP security does not work well except as a very last resort for emergencies. It hurts innovation, as we heard earlier. It doesn't scale well. You have large access control lists and lots of customer complaints. Mandatory automatic patches don't work well. It breaks too much software. There's an amazing amount of software out there that's bug compatible. Centralized management of a decentralized concept doesn't work well. But we need centralized management to solve what's inherently centralized concepts like who owns what address. Finally, we're not going to solve it by wishing the problem will go away. And if we don't solve it, well, this is what we're going to go back to. A too simple service model, and we're going to have some problems. We need scalable security solutions because wishing is not going to solve our problems. Thank you.
Our next speaker is Paul Francis. Paul Francis has long been working with us in IPv6, next generation stuff, routing. I think the number of things he hasn't done is the real question that I'd like. Paul will be speaking on IPv6 and NAT.
Okay. Thank you. I'm Paul Francis from Cornell University. I have for you today a story of woe and redemption, a story of lost opportunities and hopeful futures. This is a story which is kind of a combination between the Beauty and the Beast fairy tale and a bad romantic comedy, a very bad romantic comedy. This is the story of two star-crossed technologies that were destined by fate to come together, NAT and IPv6. You okay?
Well, I was going to make it widescreen. Can you do that?
Nope. Okay. Okay, so here's what I'm going to talk about, NAT and IPv6, their history, and sort of how they've come together in what I think is it's an interesting and in part amusing way. So this is the, this picture was kind of taken from, excuse me for a second. Okay. This down here was kind of taken from a talk that Steve Deering gave, but it pretty much shows the evolution of IPv6. This is sort of 1992, 1993 timeframe. You've already seen some of this. And there were a bunch of proposals at the time, which you've kind of heard from Dino. This one in particular, Tuba from Ross Callan, was the one that wanted to put OSI below TCP and UDP. And in retrospect, that may have been a good idea. I like this picture down here because you can follow this trail back and it gets to me. So there's this nice paper trail from IPv6 going back to me, showing that I actually had something to do with it. But in fact, the stuff that I was working on, something called PIP, had all kinds of fancy features and it was really hard to understand and stuff. And looking back, it really missed the point. And ultimately, it's Steve Deering who is much more than anybody else responsible for IPv6 as we have it today. Anyway, I think when I give this talk, it's kind of interesting because you have to get yourself in a mental framework of what it was like in the early 90s when we were first working on this problem. And sort of the most shocking thing about that was that DNS was not yet universally deployed. The IP address was the only stable long-term identifier that existed at all. Sometimes DNS worked, sometimes it didn't work. You know, it was still an, I don't know, iffy thing, but certainly a thing that hadn't really come along. So IP was very different than it is today. Today it's a kind of ephemeral, you know, address that comes and goes, and you don't need it so much. But it's really good to think back in those terms when IP was the thing that held the internet together. So with sort of that view in mind, I have this timeline that I'm going to develop as we go. And sort of on the top is the IPv6 stuff, and kind of on the bottom is the NAT stuff. And as you already know, they come together at the end of the story. But basically, there was a process. There was a group called the Routing and Addressing Group that was sort of put together by Vince Cerf that was very worried about the address depletion problem. And they did a couple of things. One is they came up with CIDR, which really fixed the worst of the address depletion problems at the time because it just utilized address space much, much better. But then they kicked off this process that ultimately resulted in IPv6 being designed and selected. It was a 2 or 3 year process and a bit painful, but that's all behind us now. At the same time, this was sort of the official line of stuff that was going on. Down here was this sort of unofficial stuff that was going on, which is basically NAT and NAT taking off. So the original NAT paper, this I do claim credit for better or for worse, happened really at about the same time frame because we were all thinking about the same sets of problems. A NAT RFC came out a little bit later, not really by my own urging, but by the urging of some people who really wanted to start deploying these kind of products. And they wanted some, legitimate paper that they could point to in their product literature. And the first NAT products started coming out shortly thereafter. Okay, so that's where we were around 1994. You kind of saw this already. As I said, IPv6 really reflects Steve Deering's goals, which are just to, basically base IPv6 on something that's already succeeded, IPv4 with bigger addresses, but in the process kind of clean up a few things that we learned over the years weren't really necessary for routing, like checksums and to some extent fragmentation and so on. There are some myths that sort of still exist that IPv6 somehow has better security or quality of service or something. These are largely not true. It does do some things sort of better, but none of these are in my mind really driving economic driving motivations for IPv6. Okay, so sort of building on the story, the next thing that I show here basically is that in the 96, when the web was really taking off, we saw really increased use of NAT and also dynamic addressing. So I mentioned these RFCs back here, which is PPP, which could dynamically assign addresses in a dial-up scenario, and DHCP, which could dynamically assign addresses in other scenarios, and obviously is taken over the world today. So I mentioned this in part because the thing I said earlier was that, back in these days, the IP address was a very permanent, stable, the only identifier we had. By this time here, around 1996, this is already starting to weaken, which is sort of freaking a lot of people out, but nevertheless, that's where the market was going. So people complained a lot about NATs, that it had these various disadvantages. And I list them here, but the first 4 don't really hold water. So one was I put state in the network, and it sort of ends this, ruins this end-to-end model. But anyway, it doesn't matter because firewalls, which is where NAT resides anyway, have state. So it's not like NAT is adding state that wouldn't have been there anyway, for the most part. Slow, expensive processing, but fortunately this all happens at the edge of the network where you can handle it a little bit better. It breaks applications that carry IP addresses, that's true, but we've since learned not to design applications that way. It's taken a long time, but I think we're pretty much there. It broke IP segmentation and stuff, but we know we don't want to segment IP anyway. So the ultimate problem is that it doesn't allow incoming connections. And I even have a caveat here that a lot of firewalls prevent this anyway, but a lot of firewalls don't. And there are a lot of cases where you want, did I skip one here? No? There are a lot of cases where the firewall would allow it if it could, but NAT prevents it. So there are cases where the fact that NAT doesn't allow incoming connections definitely hurts you. This is an interesting one to me because in this time frame there were 3 fairly important pieces of work that were done by the IETF, none of which could really deal with NAT. And all through this time frame, you know, people were moaning and groaning and complaining and whining and doing the things that IETF people do, which is that NAT has broken all of our wonderful protocols. But it was a funny thing to say because, right, NAT was invented back here, it was taking off commercially in here, and this stuff came later. So you kind of think they ought to known better by this point and not design stuff that doesn't work through NAT. And so I'm going to whine a little bit and say this is sort of a myopic viewpoint from the IETF where they just assumed that NAT was a broken technology. And the phrase really that goes about is that NAT broke the end-to-end model. And I guess I kind of thought this for a long time too, but looking back, what I think now is what NAT did was it broke a certain implementation of the end-to-end model. But there's nothing about NAT per se that is not end-to-end, and you'll sort of see why I think that's true in a few slides. So how really did NAT harm the internet, right? I mean, the internet is the big success story of the end of this millennium. So, you know, it didn't kill the internet, that's for sure. So for client-server protocols, really NAT did very little bad. You know, the big bubble was built on the client-server model as, I don't know, somebody said, Phil said, or anyway. And anyway, people came up with lots of clever ways to identify clients that no longer had permanent and stable IP addresses, HTTP cookies and all these other acronyms which you may or may not know about, but I'm not going to go through. The question really is for peer-to-peer applications, which as Phil Karn was saying, the original internet was peer-to-peer. This is what went away for a while, and now people are sort of rediscovering it like it was this great new social phenomena. This is the thing that NAT really did break. And, you know, who knows? If not for NAT, we might be having all kinds of voice over IP and funny group applications and things. We don't know. But either way, it really wasn't enough to drive motivation for IPv6. So at this sort of point in our story, IPv6 is still struggling. NAT is taking off. And I know you can't read this, or maybe a few of you can, but this is a list of sort of mutations, I'll call them, that IPv6 addressing went through to try to accommodate real-world problems that it sort of came about in the process of its evolution. So, you know, at the beginning people thought that, I guess we thought that IPv6 would naively just sort of take off, but it didn't happen. So we kept making, you know, sort of compromise after compromise to say, okay, let's try to, we'll make this protocol less clean and more complicated and stuff in the hopes that this is finally going to make deployment easy enough that something's going to happen. And these are just four of those things. So one of them I loved. When I first saw this, I had a fit because this is something called the site local address. It's essentially a private address, right? So here we have this 128-bit address space, which is supposed to give every molecule in the universe its own address, and yet we come up with the notion of private addresses anyway. I think this has fallen by the wayside in the last half year or so. But nevertheless, it was there for a long time. And it was actually trying to solve problems having to do with reassigning addresses, which actually feeds into problems of scalability, but that's another set of issues. There was another address form that snuck the IPv4 address here, which is basically used for translating between IPv4 and IPv6, and I'm not going to go into the details. This one here, Phil Karn talked about a lot because he really thought this might be the thing that kicks IPv6 off. And in this case, you embed a global IPv4 address here in the IPv6 address so that you can auto-tunnel across the global internet. There's also something called ISOTAP, which is sort of the same sort of thing, but it's for tunneling across an enterprise IPv4 infrastructure, whereas 6to4 is designed to tunnel over a global IPv4 infrastructure. And they stick the IPv4 address here. And actually, as far as I know, you can combine these two. Okay, but it gets far worse, so just hang in there. This I think is really important, which is in 1998, a full 5 years ago, this guy named Dan Cagle, who was working at an online game company called Activision, solved the NAT problem. He figured out how you could make incoming connections through NAT boxes. Okay, this is a while ago. IETF quietly ignores this. Okay, it did show up in an RFC shortly thereafter as some interesting thing you could do, but it was basically ignored. And this is actually worth talking about. So the 5-minute slide comes up, but we're in no trouble here. So the problem is this. Here's a NAT box. Here's a NAT box, right? The problem is that if somebody sends a packet, right, it gets to the other NAT box and it stops there because that NAT box has no mapping with which to deliver the packet internally to some host, right? So this is the fundamental problem with NATs. The trick is this. You have some kind of application server, okay? And say you have two guys that want to play a game, Steve here and Bob over here on their cute little devices. Basically, Steve sends a packet to the server saying, "Hi, I'm Steve," and the packet that arrives has been given the global address and port by the NAT box. Bob does the same thing. He sends a packet, and the application server sees the global address and the port assigned by the NAT box. Okay, so later, Steve says, "Hey, I want to talk to Bob." And so the application server says, "Well, Bob is available at such and such a global port and address," and then it goes and tells Bob that Steve is available at such and such a global address and port. Okay? And subsequently, here we go. Subsequently, say Steve tries to send a packet to Bob. It still doesn't work, actually, because this NAT box still doesn't have, basically it's operating a firewall function at this point. It says, no, this packet cannot come in because Bob has not shown that he wants to talk to you. But later, if Bob sends a packet, this packet will get through because the packet that Steve sent earlier sort of signaled to his NAT box that he wanted an outgoing packet, and subsequently the packets can flow. So sort of my question, regarding the end-to-end model is, why is this not end-to-end? Okay, you have two guys, they're sending IP packets to each other, they're fully aware of the addresses and ports that the other guys are using. You can quibble that this is not the IP instantiation of end-to-end, and it's not, but it strikes me as an end-to-end model nevertheless. Okay, nevertheless, there are limitations with this approach. It doesn't work through all kinds of NAT boxes, but I would argue that this is because nobody sat down and told the people building NAT boxes not to build them this way because there was this cool trick you could do. So we kind of ignored the problem and nothing happened. It doesn't work for TCP, usually because TCP is kind of a client server. It sort of expects a listener and a connector, and if you remember my picture, it really required that both ends initiate a connection. At Cornell, we're sort of working on this, and I actually think we have a fix to this problem, so it's kind of interesting, but we'll see where that goes. And there's a bunch of corner cases where it just doesn't work well, but I still think this is because of lack of attention from the standard community as opposed to a fundamental problem with NAT. Anyway, 2 minutes, oh my goodness. So there was an interesting sea change in the attitude towards NAT quite recently, in the last couple of years. So I said before, there's these protocols that didn't work with NAT. Well, mobile IP has now defined how to run over UDP. SIP is now defining how to get through NATs with protocols called stun and ice. IPsec is defining also how to tunnel through UDP. So this is all starting to happen, and people are finally starting to say, hey, we could have designed these protocols to work through NAT in the first place. Duh. So, yeah, so the world is getting NAT friendly. The suite of protocols for SIP, they sort of use the technique by Dan Cagle that I showed before. They don't allow peer-to-peer TCP connections, again, because TCP is not a symmetric protocol. The one I like best is called Teredo, and this is sort of the, what I'm finally getting to in my story. This is the definition of IPv6 over UDP in order to get through NATs. And it will work with TCP and UDP as long as they're running over IP6. So it means that you have to have changes in the OS to make this work, but that doesn't seem to bother Microsoft. So this is the Teredo stack. Okay, like I said, it's IPv6 over UDP over IPv4, and NAT boxes recognize this portion, so it works through NAT in the same way I just described. And this is what the IPv6 address looks like, and this really takes us full circle, because here we have the global IPv4 address of the NAT box. We have the UDP port that it's running through. We actually embed the type of NAT, and then we have another IPv4 address, which is this sort of application server role that I was kind of describing before. It's the globally addressable box that's able to tell both parties about this address. This I think is a very lovely address, and it really represents how far the IPv6 people are willing to bend over to get people to use this protocol. Anyway, the status. Okay, that was mean, wasn't it? Okay, so Microsoft is kind of pushing Teredo. They've got it in a peer-to-peer toolkit. The thing about Teredo is, I mean, even Phil Carnes talk about 6-to-4. It required that your firewall understands 6-to-4. Teredo doesn't require anything except a company that's willing to put a Teredo server out there. So all you need is an IPv4 host, well, an IPv6 host running Teredo, and no help from the infrastructure, and the thing will work. The SIP community is moving ahead with their SIP-related approaches. Where IPv6 is going, different people have different opinions. I still think that fundamentally there's not an economic foundation for IPv6, and this is going to kill it in the end. But, I've only been saying that for 10 years now, so I could still be wrong. This is my last slide. So what I would kind of like to see happen and sort of hope to see happen is that the peer-to-peer community, maybe through the auspices of IETF, finally settles on a STUN or a Teredo-like approach and says, okay, let's just accept this. Let's write it down. Let's get the firewalls and the management tools and everything else to buy into one way of doing this. And finally, we can see some uniformity in the sort of solution that comes along. What I'm a little bit worried about is that still the sort of standards folks are going to ignore this, are still going to try to push IPv6 in its most pure form, and there's not going to be convergence, and so things are still going to be pretty fragmented and not work well. But anyway, that's my story, so we can take questions later, I guess.
Oh, actually,
Thanks.
now's the question time. Dino? Dino? Any people from the Retro Talks today? Phil, Dino, Steve, John, if you're still, John Karen, all the rest of the folks who had Retro Talks this morning. This is the time to say, so why did you build it that way? And I'll start out with a few of those points to remind you where we were. Scott told us about the 7 virtues of IP. I actually found 7 virtues, not 7 deadly sins. You can grab. Phil told us that it's really good, end-to-end is good for apps. On the other hand, Paul says NAT's good for us. You can see that there's still quite a bit. So we'll take questions on any of this. If not, I'll start off with some, but please step to the mic, find something interesting, and ask away for these panelists.
Hi, I don't have a question, but I have a story, since Sue's really keen on stories today. Do we have a minute for a story? My name's Kathy Whitbrodt, and a long time ago I worked with Sue Hares at Merit, and it's not too embarrassing, Sue, but I couldn't resist. So there was this really nice man in Canada named Tom who worked on the CANet backbone. And for those of you who don't know, Sue used to single-handedly can generate the configs for the policy database for the NSFnet, seemingly and miraculously by hand for quite some time, because EGP was breaking everything and the regional networks were looping with each other, and it was kind of fun for me because routing was new. But anyway, so one day Tom decided that he would TFTP the password file from merit.edu, and he would see if he could crack some of the passwords, in a nice, neighborly sort of way. And he discovered many of the passwords, including the root password, which was Michigan. So, so at the same time, Sue, unaware of Tom TFTPing the merit.edu password, was off generating the configs for the NSFnet backbone, and just so happened to mistype something and knock Canada off the network. So, so Tom's sitting in his office, and his office mate comes in and explains to him that he better start polishing up his resume because apparently in retaliation for him TFTPing the password file, which Sue was unaware of, CANet was completely, the whole Canada network was completely unreachable from the U.S. So anyway, it was just kind of fun. So soon after that, things became much more automated, but in the beginning, it was sort of a quick stopgap, and it was a lot of fun. Anyway.
Don't mess with Sue, yeah. So John says,
Should I go to another mic? I don't know what this first acronym means, so if this question is not interesting, just say so. ASM is working for many applications, such as the access grid. Why isn't this good enough? Why do routers need to support SSH and BIDR and get off of ASM? Is that interesting?
Dina?
Yeah, well, I don't know if it's interesting, but I could answer the question. I assume the question is, we're dependent on ASM right now, and it seems like there's forces pushing us in other directions. Is it going to be easy to convert? I think it can be, but it's a question of the number of things you want to change. We just had a hallway discussion saying that you could take an ASM core and have the end nodes not do anything different and just convert the core to be BIDR, and that would be a simple way of solving that problem.
This question's for Dino. Dina, do we have a connectionless or a connection-oriented network at this point?
We have an end-to-end connection-oriented network with a datagram core.
Anyone else want to make any comments? Scott?
Oh, I think Dino's answer was almost perfect because it conveyed just the right lack of information.
Okay. Bill?
I remember there was a time when the biggest debate was, is it OSI or is it TCP? Which stack won?
Well, what didn't win was the OSI standardization process, which brought us X400 and X500 and all of those other carrier-centric services. I don't know whether OSI or TCP/IP won in a more fundamental sense. Certainly the packet format didn't change. I will say that when Allison and I did this is what V6 is going to look like, the first place we went to tell about that was NIST, the OSI folks at NIST. And after explaining what V6 looked like, the first question we were asked was, why didn't we approve something that had been adopted by an international standards body? We said we had. They didn't agree. But then all the rest of the questions were, how are they going to convert? And we told them they converted by using OSI NSAPs in IPv6 addresses. And if you look, there is an experimental RFC to tell them how to do that. Take that 20-byte NSAP and stick it down into 14 bytes. It shows you how much content there's there. And they were just tickled pink that they were going to be able to do this, because it would preserve all of the investment they'd done in addressing plans. I don't think it was ever used, but boy, was that important.
There was a saying a number of years ago that I don't know what the programming language of the future is going to be, but it's going to be called Fortran. Well, time has changed. It's now going to be called C, or C followed by some suffix. But I've also heard the same said about the internet, that networking protocol of the future will be called TCP/IP, regardless of what it looks like.
Scott had an ideal point there in terms of carrier-centric nature of things, which I actually got up to comment on Paul's talk and get some feedback here. But carrier-centric actually fits into the NAT and NAT traversal rendezvous structure that Paul described, in that it provides a place that the carriers have to go, can grab control again. right? The end-to-end is not really there because the endpoints aren't in control. The carrier rendezvous point is in control, right? So in your talk, you said that V6 doesn't have an economic base, but in fact, you described it and you stepped right over the top of it. It is in the application space because the application sees a consistent network address, whatever the structure of the bits is. This community would see the structure of the bits and pay attention to routing, and economic basis is harder to define. It's probably more in the aspects of efficiency and whether you're tunneling or how many bytes of header and all the efficiency space there. But the application developer in his space only sees 128-bit address, and it's consistent whatever that means. Right? So your comments on that.
Tony, just a quick comment on that first. There's nothing that says that rendezvous point has to be run by a carrier. It can be run by you out of your basement, as long as you don't have an NAT in the way.
Well, as long as I don't have a NAT in the way, but I do. So in fact, look at what the carriers are going to do. They're going to grab that rendezvous point and make it the thing that is the control point. Because that's the only way you can get connectivity behind your NAT is to go to the central server that is the control point.
But Microsoft runs one of those servers. Anybody can run one of those servers. You just subscribe to it. It doesn't have to be a carrier. That's my point.
I would put out the following, which is that today, most applications don't look at the IPv4 address, they just look at the domain name.
Or
if
go
it's
look
zip,
again.
Hang on, it's something like that.
Well-written applications,
so
I agree.
The first thing that happens, right, is that it goes to DNS, which is not quite the same as the box I described, but nevertheless, it's a box out there that sort of sets up this binding for you. So it's got some similarities, but this hasn't, and the fact that the carriers do run these DNS servers, hasn't in many ways broken that model. So there may be something to what you say, but I don't see why this is an economic driver for IPv6 in any event.
Well, the question is, where's the economic driver? And it's not in the routing space. If you're focused in the routing space, you're not going to find an economic driver. If you're focused in the application development space, efficiency at that level and understanding a consistent addressing model is probably where you get efficiency. Where you can't get it quite as easily, you've got to build in all this infrastructure for NAT traversal and various schemes.
Bill? Oh, excuse me. Lots of people. My apologies.
Tony, just to pick up, I don't know whether or not IPv6 provides an economic driver for carriers to deploy it. My views on IPv6 are documented in RFC 1669 in 1994. So you can go pull those, they haven't changed any. The fact of the matter is that we're going to need IPv6 at some point, and at that point we'll deploy it. I think one of the more interesting aspects is IPv6 is going to provide a clean slate for deployment models. And the fact that we deployed a worldwide internet with IPv4 and we have no authentication and no way of tracking back who's on the end of an IP address sort of also contributes to why we have 2,000 spam messages an hour coming into our mailboxes. I do not think when IPv6 gets deployed for real, you're going to see the same mistake.
But what do you think will improve in the security, John, on that? And Steve, if you want to pick up some of that as well.
On Steve's slides earlier on security, we saw a number of issues. One of the ones we didn't see actually in that list of what is security is authentication. The fact of the matter is that until you can hunt down the responsible party of a packet, a stream, or a message, you have no recourse. And IPv6 is an opportunity to reset the expectations there. And I think there'll be a lot of work in that over the next few years to ensure that when a robust worldwide IPv6 network is built, it's actually robust.
John, I don't agree. It's
I know, Steve.
But you knew that. Authentication is a means to an end. It's making your access control decisions. And it comes down to authorization. Who is authorized to send you email? I personally don't want a world where I have to be a customer of one of the 20 or 40 whatever biggest ISPs to be able to send email. There are lots and lots of reasons that don't even have vaguely to do with the end-to-end principle, although that's a good part of it. What is an ISP? Who is authorized? And that's the real issue with the spam. People are sending mail to me that I don't want them to be authorized to, and they just change their name or hack someone's PC the way they're already doing today. I don't have to assume that. They'll still be sending spam. Remember the security problem was buggy code. That's not going to go away with V6 either. They'll hack people's PCs that are authorized to send email.
The compromise between you two is static allocations to each customer. Think static allocations, you now know exactly which customer to go talk to, right? With V6, you get that ability to have a static allocation, where with the V4, you're into dynamic space and you have to do this time correlation crap.
Can I change the subject for just a minute?
Go ahead.
I am not an American Airlines pilot, but I'm going to ask a question of the general audience. How many people are creationists? How many people are Darwinists? One of the recurring threads that seems to have gone through today's sets of topics are, this is an evolutionary activity, no flag days, none of this other stuff. And this jars with my memory. There was an imp over here, and there was the footprint of the multiple RTs that was the NSF net. There was the BGP3, and then every ISP sat around a table during an IETF, and we all turned on BGP4 and turned off BGP3.
So we had
Remember
a hammer,
flag
we hit
days.
ourselves, and we said it's good when we stop?
I remember flag days occurring, and those are part of the, for me, the evolutionary cycle. So I'm thinking that this idea of this sort of smooth, seamless transition where we can sort of seamlessly, amoeba-like adopt and absorb new technologies and new techniques is a fallacy. I think that there are disruptive things, and we're approaching several of them. And as a community, if we become complacent about our level of expertise with IPv4 and the existing routing protocols and the existing mindsets, we are going to be rudely interrupted in our thought processes as some of these new things come into fruition. So if you look to the past, I'm thinking that you need to extend into the future a little bit and say it's not going to be this nice, simple path. There are going to be some really interesting times ahead. And so be agile and be prepared.
I think tomorrow morning you'll find some interesting times ahead in the BGP stream. Bill, did you have any other specific technologies that you felt we're going to have, like DNS?
I made the mistake of going to Hawaii a couple of weeks, well, I guess it was a week ago, and listening to Dave Clark tell the academic community that the internet, the guys who developed the internet, on Scott's slide this morning there was that grainy picture of a bunch of guys sitting around a table in white suits and ties.
No ties at the imp christening, which is what that picture was.
Okay, whatever. But that group of folks, right? One of those people stood up and said, we should have shelved the internet before we turned it loose on the commercial world. We should have left it as an academic plaything. He suggests that the internet of the future is going to be less driven by individuals and more by avatars and machines talking to each other, and so the ideas of communities of interest and rethinking the end-to-end principle are going to be fundamental. And so the ability to in fact reach out and touch 200 million nodes is probably not going to be something that happens in the future. Authentication and integrity of the data flows are going to be interesting when machines start talking to machines. This may be the wrong forum for those kinds of things. So for the wisdom of the ages that's the panel up there, what do you think? What's the future?
I think things can change. How many cell phones have you owned in your lifetime? How many different cell phones?
More than 10.
I think there's this.
The answer was more than 10.
So I think as long as there's new technology and there's always a one-up that provides new features, even if, you know, you're buying a cell phone because it's turquoise rather than what it can do, there's always opportunity to do things the right way.
Next question back there, and then that one on the left-hand side. I just can't see behind the lights. I apologize.
Pete Krukenberg with Utah Education Network. I have a comment and then a question. We've seen in our network where, since we're an academic research network, and we don't suffer from the address shortages that most of you probably do. While I agree that NAP may not necessarily disrupt end-to-end connectivity it certainly has a dampening effect, particularly in innovation of new services. And I'm not sure that that dampening effect is much different than the dampening effect that a centrally controlled network has. That was probably not as significant. My question is, looking at what the broadcast industry went through with HDTV, and the fact that they talked about that for a pretty long time, like we have about IPv6, is IPv6 more an issue that needs to be decided by someone else like the FCC, or can the industry actually make that transition? Will we spend all of our time figuring out how to stay on IPv4 until somebody makes us move to IPv6?
Go ahead, John.
I have an opinion here. In the middle of your question, you said, should IPv6 be decided by someone like the FCC? Recognize the internet is global. The FCC is an important organization, particularly for a lot of us. But at the same time, transitions like this are going to have to be led by the technical community, and I mean that both by the IETF and the vendors that implement the protocols in their equipment, and the operators, and it's going to be a consensus kind of operation. The challenge you've got is, I don't believe in a flag day for IPv6. That's a little too exciting. Right now, we don't have a challenge. CIDR was deployed, and it has cut down the rate of IPv6 deployment, IPv4, to the point where we don't have this, edge of the cliff approaching us. And so you don't feel the pressure. The good news is, I'm not going to say we're ahead, but we're actually kind of on schedule. As noted earlier, IPv6 is in a lot of the devices sitting out here in the audience, and it works. Okay, so when we go to use it, it shouldn't be too bad. I mean, we're going to find some fun problems, because you always do. But it's not going to be a nightmare. The code base will not be pushed out at the last minute. So I think IPv6 will begin to appear in more and more islands, and those islands will get interconnected. The challenge we have is, when do we get to the point where the internet is IPv6 and an IPv6 only host can survive? That's a different question. That does depend on something like NAT for quite some time. And I think we're going to have both for a while. But, one will push out the other over time, just like one operating system on your laptop gets replaced another. Sooner or later, might be 20 years from now, we'll begin to see pockets of IPv4 disappear. But it's still a ways off, and we don't have to worry, because we have cut down the address allocation to the address allocation policies in a way that makes sense in a more flexible format with CIDR.
Any other panelist answer?
Yeah, I guess I just want to say that, I don't mean to be quite characterized the way Sue did by saying, flat out NAT is good. It has had a limiting effect. I just wanted to kind of say that in part that's because, the people developing this technology refused to take it seriously until they really had to. And in the last 5 years, there's been a lot of cool innovation with how to work with NAT, and I think if people had had the attitude from the beginning that they should figure out how to work with NAT, things might have been a lot better a lot sooner. That's all. As far as the HDTV thing goes, I guess I would argue that when I look at my TV and it's HDTV, it looks a lot better than the other one, but if I look at my computer screen and it's IPv6, I actually really can't tell. But it's obviously more subtle than that, but anyway.
Around 1990, 1991, we're having a discussion in the cafeteria at Bell Labs one day, and we talked about what would later become known as NAT. We concluded that this was a difficult to do idea and probably wasn't feasible, which shows why I'm not in the prophecy business. I was one of the proponents of that view. Good idea, NATs are partially response to shortage of address, partially response to, my ISP wants to charge me extra for more addresses, partially response to, I have to renumber if I switch providers, and partially to some people they think, this is my firewall, this is protecting me, but the nice generic tools we have for punching holes in NATs, the next generation of worms is going to know how to manipulate those protocols to, I want to put a backdoor on 3127? Great! I'll have this NAT box open up 3127. Why not? I have a nice generic protocol to do so. So one of the really useful things that NAT is doing is going to go away pretty soon. So leaving us with the artifacts.
We're going to pick up Scott, and then we're going to go to this question back here. Tony, we're going to hold, because I promised.
All I had was one comment.
No,
about,
but we're
about,
good.
no, I understand. I'm just one comment that's related to this
After
current
Scott,
question. So,
if it's 2 minutes and it's
Yeah.
Scott first, then you, then I can't see in the dark here with the lights on my, go ahead.
Being a little sarcastic, actually, V6 has been quite stunningly successful without being deployed.
Okay.
We really don't have the we're running out of IP addresses panic that we had back in the early 90s, not simply because of the reasons John suggested, because the running out of IP address panic had really nothing to do with facts. It had to do with the perception of the press and the perception of the VC community saying we can't invest in IP because we're running out of IP addresses, when really the only thing that Frank Slinsky said was we're running out of IP Class B addresses, IPv4 Class B addresses. So that whole mythology has gone away, and you really don't see that anymore. Maybe it's because we have this thing waiting in the wings. Maybe it's because people have just been lazed out of it. But still, I'd consider that a success. V6 has made it so we're not running out of IP addresses in the minds of the people that don't understand the problem.
Well, that's because of
And
that.
then the second thing is that we don't have the ISO IP wars. Whether the right answer came out or not, it depends on your point of view. There was an awful lot of energy expended building parallel stacks in the standards bodies and in the vendors. DEC spent a few $1 billion on it. IBM spent in that same range, and it tanked, and it was a huge waste of resources. So I'd say that V6 has actually been quite successful, getting rid of two very things that were pretty hard on us. The running out of IP address concept and the ISO IP wars. And maybe it's a good protocol too. We'll have to see that.
Tony, short comment?
yes, specifically to the question about HDTV and whether the FCC should be on this, there is a Department of Commerce request for comment out there right now, and it asks exactly that question. If you have an opinion, you probably want to express it.
Go ahead, please, your name.
John Larson, Sprint Labs. I just wanted to add a data point that I've discovered a few minutes ago to the importance of security and availability threats to the future design of the internet. I've been trying to use the broadband connection in my room, actually 2 different rooms. It's been down for the last couple of days. So I talked to the manager and talked to the tech support guys to find out what's going on. The answer today is that the hotel computers are all infested with worms, in particular MyDoom A. And so that's been the problem today, at least. So it's certainly affecting me personally.
That's a good comment to end on. Thank you very much. I encourage you to talk to the panelists. I want to again have a round of applause for all of these